Anti-reflection coating. As we have studied in earlier lectures that when the light passes through the glass, it is partially reflected and partially transmitted. So what happens in this case? The intensity of the reflected light as well as the transmitted light reduces because of partial reflection and transmission. However, optical instruments such as telescopes, microscopes, and cameras. In these instruments, there are multi-component lenses used. Several lenses are used in such a instruments, in such a optical instruments, and in that there would be multiple reflection of the light. Since there are several glass lenses are used, there would be multiple reflection of the light waves from these lenses, and images produced by these instruments then can be poor because there are several glass lenses used. Every time there would be partial reflection and partial transmission. At the end, you will get very poor image. So what happened in the year 1935? Scientist Jena discovered that the phenomena of interference can be used to suppress reflection by coating it with a thin transparent film. So we can suppress the reflection. You can suppress the reflected light by coating it with a thin transparent film. And such a thin transparent film which coated on surface of a glass, which is lens, to suppress the reflection from it is called anti-reflection coating. So as shown in this diagram, you can see here that this is the lens which is of the material glass, and on this material the thin film which is the transparent film coated. So when light is incident on the film, as you can see, it is partly reflected as a ray 1 and partly reflected as ray 2, and it is partly then transmitted through the glass lens. So what we want here, we have coated this film to suppress the reflected light. So there should not be ray 1, ray 2, which are the reflected light. There should not be ray 1 and ray 2, and all the light should be transmitted through the glass lens. So that you can get only when ray 1 and ray 2 are interfered destructively. Ray 1 and ray 2 should interfere destructively, and both the rays should have equal amplitude. So there are two conditions to suppress the reflected light. So let's write that a thin film acts as anti-reflection coating if there are two conditions. The first condition is called the amplitude condition, and in this amplitude condition is nothing but the reflected waves should have equal amplitude. Then only there would be complete destructive interference. And this condition is called amplitude condition. So in this case, as we see in this diagram, ray 1 and ray 2 are the reflected rays. Ray 1 is reflected from the top surface of film. Ray 2 is reflected from bottom surface of the film. And the film thickness is shown over here is T. So in this case, amplitude of ray 1 should be equals to the amplitude of ray 2. Then only there would be complete destructive interference. So this condition is called the amplitude condition. So when the thin film satisfies this condition, then it can act as a anti-reflection coating. And the second condition is waves which are reflected, as we can see here, waves or rays, let us say rays, reflected rays from top and bottom surface of film should be out of phase by 180 degree. If they are out of phase by 180 degree, it means that ray 1 and ray 2 will interfere destructively. So this is this condition called phase condition. So when these two conditions, the condition is amplitude condition and the second condition is phase condition. When this film, which is coated on the glass, satisfies amplitude condition and the phase condition, then only that film will act as a anti-reflection coating. Okay, the anti-reflection coating should satisfy amplitude condition as phase condition. Both the conditions should be satisfied, then only that film will act as a anti-reflection coating. So let us see what is the condition, amplitude condition. The first condition is amplitude condition. Now this amplitude condition means ray 1 and ray 2 should have equal amplitude. Let's say ray 1 amplitude is E1 and amplitude of ray 2 is E2. So in amplitude condition, E1 should be equals to E2. And for this condition to be satisfied, it requires reflectivity of film and reflectivity of glass should be same. Reflectivity of the film from which ray 1 is reflected and reflectivity of ray 2 from the glass surface. Here ray 2 is reflected from the top surface of the glass. Ray 1 is reflected from top surface of the film. So the reflectivity of the film for ray 1 should be equals to reflectivity of the glass for ray 2. When their reflectivities are same, when the reflectivities of ray 1 and ray 2 are same, then ray 1 and ray 2 will have equal amplitude. And the reflectivity is given by the reflectivity is given by, so reflectivity of the film. For that, let us say that mu A is refractive index of air. Mu F is refractive index of film, and mu G is refractive index of glass. Then reflectivity of the film is given by mu F minus mu A, refractive index of the film minus refractive index of air, divided by refractive index of film plus refractive index of air, and square of this. So this is the reflectivity of the film, and this should be equals to refractivity of the glass. Refractivity of the glass is given by mu G minus mu F, that is refractive index of glass minus refractive index of film, divided by refractive index of glass plus refractive index of film, and square of it. Okay, so this is the reflectivity of the glass. So reflectivity of the film should be equals to reflectivity of glass, and we have to solve this equation. Let us solve this equation by taking the cross multiplication. First, let us take square root on both sides. And substitute mu A is equals to 1. Then you will get mu F minus 1 upon mu F plus 1 equals to mu G minus mu F upon mu G plus mu F. Then let us take the cross multiplication and rewrite this equation as mu F mu G, this term into this term. So you get mu F into mu G plus mu F square minus mu G minus mu F. That is equals to, then we will take the cross multiplication of this quantity, which is equals to mu F mu G minus mu F square plus mu G minus mu F. So here in this case, this term cancels with this term, minus mu F cancels with this mu F, and what you get is 2 mu F square is equals to 2 mu G, or mu F is equals to square root of mu G. So you will get the same reflectivity of the film and the glass if refractive index of film is equals to square root of refractive index of glass. So you cannot select any material as an anti-reflection coating. You have to select the material to act as an anti-reflection coating whose refractive index would be equals to square root of refractive index of glass. Then only that material will get, from that material you will get same reflectivity. That means reflected rays will have equal amplitude. Then let us see the second condition. The second condition is phase condition. In the phase condition, as ray 1 and ray 2. Ray 1 is, as you can see here, ray 1 is reflected from the film and ray 2 is reflected from the glass surface. So these ray 1 and ray 2 should interfere destructively, and for that ray 1 and ray 2 should be out of phase by 180 degree. That is, ray 1 and ray 2 should interfere destructively. For that, let us first find the path difference between ray 1 and ray 2. See the diagram here. There is a thin transparent parallel film here. This is the film, which is a transparent parallel film. And you already studied the path difference for thin transparent film in the reflected light. So the path difference in this case between the ray 1 and ray 2 is, we already derived that derivation. So the path difference between ray 1 and ray 2 is given by this equation. Delta is equals to 2 mu t cos r. But in this case, mu here is the refractive index of the film. And we denoted refractive index of the film by mu f. So 2 mu f t cos r is the path difference between the ray 1 and ray 2. But we have to also consider corrections. Correction is if ray or light is reflected from denser medium, its path changes by lambda by 2. So we have to check ray 1 and ray 2 if they are reflected from the denser medium. For that, let's see the diagram here. As you can see in this diagram, the ray 1 is reflected from this point, that is from the film. This is air here, this is film, and this is the glass. So ray 1, as you see here, is reflected from the denser medium, from film. Film is the denser medium. So there would be change in the path of ray 1 by lambda by 2. Then let's see ray 2. Ray 2 is reflected from this point, that is from the glass surface. With respect to film, the glass is denser, as we have proved that mu f should be equals to square root of mu g, means refractive index of glass is more than refractive index of film. So for film, with respect to film, the glass is denser medium. So ray 2 also reflected from the denser medium. So both the rays in this case are reflected from denser medium. And what we are writing here is the path difference. So path difference delta, which is 2 mu f t cos r. For one ray it is lambda by 2, for another it is minus lambda by 2, because you are taking the difference in the path. So lambda by 2 minus lambda by 2. What you get is delta equals to then 2 mu f t cos r is the path difference between the ray 1 and ray 2. And what we want in this case is this path difference should be equals to odd multiple of lambda by 2 for destructive interference. Since we want to suppress this ray 1 and ray 2, so ray 1 and ray 2 should interfere destructively. So the path difference is 2 mu f t cos r should be equals to 2n plus 1 lambda by 2. This is nothing but condition to suppress reflection. So they interfere. There should be destructive interference of the reflected light, and there should be complete destructive interference of the reflected light. Then only all the rays, all the light will be transmitted through the glass. Let us consider for normal incidence. For normal incidence, R should be equals to 0. And for minimum thickness of the film, you cannot deposit thick film on the glass. The thickness of the film should be minimum on the lens. And for minimum thickness of the film, that is for T minimum, N should be 0. This N should be 0 for minimum thickness. Then let us rewrite the equation 2 mu f t. The cos r is 0, so cos r is 1. That is equals to lambda by 2 because n is equals to 0 for minimum thickness. So I will write that thickness is minimum when n equals to 0. Let us rewrite this, then mu f into T minimum is equals to lambda by 4. And this mu f T minimum is nothing but optical thickness of the film. So optical thickness of film should be equals to the quarter of the wavelength. If it is a quarter of the wavelength, then there would be destructive interference. Ray 1 and ray 2 would be out of phase by 180 degree. It means they will interfere destructively. And there would be complete interference because the amplitude condition is also satisfied. We have selected the material whose refractive index would be equals to the square root of refractive index of the glass. And the thickness, optical thickness of the film is equals to the quarter of the wavelength. So when these two conditions are satisfied, there would be complete destructive interference in the reflected light. So here the intensity would be 0 and all the light will then transmitted through the glass. There won't be any reflection from the glass surface. So when these both the conditions are satisfied, then that coating will act as a anti-reflection coating to solve the problem, or if you want to find the minimum thickness, then you can write this T minimum is equals to lambda upon 4 times mu f.